My name is Aurin Sarcar, and I'm going to be going over a concept in chapter 11.4, and that topic is the cross product. So what is the cross product? Let's talk about it geometrically before we go over it algebraically, right? So basically, in terms of just geometry, what it is if you have two three-dimensional vectors, right? Let's say we have these two, and this will be the z-axis, this will be the x-axis, this will be the y-axis. What it essentially is, right, is when you take the plane that these two vectors share and you create another vector that is perpendicular to that plane, or in other words, is orthogonal to those two vectors. More accurately, is orthogonal because it's a three-dimensional vector. Basically, that is their cross product. And the magnitude of this new vector is going to be equal to the parallelogram area formed by those two initial vectors that we had that we're taking the cross product of. So for example, let's say we have u and we have v, right? So these are going to form some sort of parallelogram. Let's use a different color for that. These are going to form a parallelogram, and that parallelogram is going to have some area, right? This area, which would be u times v, magnitude of u times magnitude of v, rather, times sine of the angle between them right here. That is going to give us the magnitude. So that's going to equal magnitude u cross v. And you can prove this yourself. I don't have enough time to explain the proof, but if you'd like to find the proof, you do it using the distance formula. So you'd start with u cross v, and you'd square it so that you can square the other side. And we'll get to what goes on this side after we've discussed the algebraic representation of the cross product. So let's go u cross v, right? U cross v is going to be equal to u2 v3 minus u3 v2 times I, which is the x component, minus, very important to remember that this is minus and z will be plus. So for the y-axis, it's minus u1 v3 minus u3 v1 j, plus, like I was saying, u1 v2 minus u2 v1 k. Okay, so this is the basic cross product formula. And when I'm saying it goes here, right here, this would be, you take that formula, and instead of focusing on I, J, K, we don't care about the directions when we're working with just magnitudes. And this is going to be a magnitude, which is a scalar quantity, not a vector. It's going to be a scalar quantity, right? So we can ignore I, J, K, and we're just going to square the magnitude in each direction, basically, because that's how you use the distance formula. So u2 v3 minus u3 v2 squared plus, and this minus becomes a plus over here because we're squaring, right? So we can do that. So u1 v3 minus u3 v1 squared plus u1 v2 minus u2 v1 squared. So if you take this and you continue to derive downward, and you'll have to do a little bit of special addition and subtraction along the way, you'll eventually get it into a form where you have something like a plus b plus c squared. And then you're going to have to use polynomial expansion on that. And once you expand it, you'll eventually see that you can kind of bring it back to this form. I don't have time to go over the whole thing right now, so I'm just going to skip it. And let's quickly go over how to do a three-dimensional vector cross product using a matrix. So that would look something like this, right? We'd have obviously our unit vector at the top, I, J, K. Then we'd have u1, u2, u3. We'd have v1, v2, v3. So when we're working with this, right, we're going to take one unit vector component. So let's say we take I, right? We'll cross out the row and the column that it's from, and we'll be left with a two-dimensional vector array. A two-dimensional matrix, which we already know how to solve for that in terms of cross product. We go top left, down to bottom right, but top right down to bottom left, u2 v3 minus u3 v2. We know that from pre-calculus, so we can just apply that, and it'll look something like this. v3, sorry, u2 v3 v2 v3. Remember, minus when you're going onto the y-axis, and then plus when you're going onto the z-axis. So I'm just going to quickly duplicate that. Let's turn this into j, and this will be 1 and 3. Yep. 1, and then finally we're going to get k over here. That'll be plus k, and that'll be 1 and 2, right? Right. So this is how you do it with, expanding the matrices, and that helps sometimes when you can't remember this longer formula. So anyway, let's hop into the algebraic properties. I'm going to number them off real quick. There are 6 main ones that you're going to want to remember, and for a couple of them, the proof is very easy, so we'll go over it real quick. So we have u cross product v equals negative of the flip of that. Negative v cross product u. So this is very important because the order of the operands of a cross product matter, and it's for a lot of basic operations that doesn't matter, but for this it does. So the next one is u cross v plus w equals u cross v plus u cross w. And you might be wondering, why is that possible? It sort of works kind of like the distributive property, right? So earlier we were talking about how cross product finds us an orthogonal vector, right? So a vector that's orthogonal to this composition of vectors would kind of be the same thing as finding one orthogonal vector, another orthogonal vector, and then you add them together, right? So, that makes logical sense. And then this one's also very easy. Cu cross v equals Cu cross v equals u cross cv. This makes sense because basically what would happen is this c right here, right? This c would just become a coefficient in every single term, right? And you'd eventually just get to pull it out over here outside all of them. And after that, you could just put a big fat parenthesis around everything and say times c. So, for that reason, you can kind of just, you can distribute that c to whichever coefficient, or you can just put it out here. All right, and the next one we want to worry about is u cross 0 equals 0, and u cross u equals 0. These two, we can think about the parallelogram from earlier, right? You can prove these algebraically pretty easily, but I think the easiest way to think about it is, you have this initial vector, right? If we have 0, then there's nothing to make a parallelogram out of. And if we just have another vector that's, the same, it's like a flat line for the parallelogram. So there's also no area in that parallelogram. So we can actually even think about like a scalar multiple vector of this, right? Of our initial vector would be something like this, right? Or it could be longer, but either way, it would basically just form a line with the other vector. So even for scalar multiple vectors, there's that property that, it'll have a cross product of 0. And then let's go over the final one, which is u dot product v cross w equals u cross v dot product with w. And remember, the order matters for this. Now, this actually has a special name, right? And the special name for this is it's the triple scalar product, okay? The triple scalar product. And it's called that because it'll ultimately be scalar because, we're taking a dot product at the end. So keep that in mind when you're taking the triple scalar product. And that basically looks something like this. It'll be like u1, u2, u3, basically where I, j, and k would have gone, you're going to put in u's values instead. So anyway, and just to be clear, that would be this side. Now, the reason, real quick, let's just prove this one because this one's also very easy to prove. Number one. So the reason number one works is let's just quickly pull down our initial cross product formula, right? So just when we're solving for I, right? If we're starting with V, then it'll be V2 U3 minus V3 U2, right? And if we take this, right, if we take a good look at it, what's common between these two? If we reorganize the terms, right, to have U in the front, it'll be U3 V2 minus U2 V3 over here. So these two are equal. And what that basically gives us, right, is negative U2 V3 plus U3 V2 I, which is nothing but negative U2 V3 minus U3 V2 I. And, that same pattern repeats for these two parts. And so V cross U is going to be the negative version. And it's very important to understand that, like most operations, you can't just have, you can't just flip the operands. Now that we've gone over that, let's quickly go over a couple of geometric properties that we might not have covered earlier. I covered most of them when I was talking about the parallelogram. I'll just rehash real quick. 1, 2, 3, 4 main geometric properties exist. And those are 1, U cross V is orthogonal to U and V. To U and V both, right? Which, again, refresher, orthogonal is like perpendicular in a 3D space. Then cross product U and V, it's that the magnitude of that is equal to magnitude of U times the magnitude of V sine theta. Then, and we went over this earlier. We skipped the proof, but you can totally prove it on your own. It would be very helpful. Then U cross V equals 0. If U and V are scalar multiples of each other. That was when I was explaining like this. There's no area to make a parallelogram, so, right? And then cross of U and V, the magnitude of that equals area of parallelogram where sides equal U and V. So it'll look something like that. And the reason that is obviously is because this is, if you remember from trig or from geometry, this is the area of a parallelogram. So now that we have the basic geometric properties, let's go ahead and solve like a basic cross product problem real quick. I think that's about all the time we have left. Let's go and do U equals I minus 4j plus k, and V equals 2i plus 3j, which means it equals 2i plus 3j plus 0k, right? And now let's quickly build out that matrix that we had earlier so that we don't have to bring back our formula. I, j, k, unit vector on the top, right? And then we'll put our first vector first. Just to be clear, we'll do U cross product V because like I said, the order matters. So U cross product V, so it'll be U1, U2, U3, V1, V2, V3 equals I, J, K, it'll be 1, negative 4, 1, and 2, 3, 0. And that'll give us these 2D matrices. Hold on. It'll give us I, negative 4, 0, 1, 3, minus, remember, don't forget that, J, 1, 1, 2, 0, plus K times 1, negative 4, 2, 3. So let's real quickly evaluate this. This will give us 0 minus 3i minus 0 minus 2j plus 3 minus negative 8k, right? If we do the multiplication. And that'll give us negative 3i plus 2j plus 11k. And there you go. There's our answer to that cross product.